Let's talk about another property of elements as it relates to ion formation, their ionization energies. If we start with an isolated, neutral atom of some element in the gaseous state, which is not the normal state for most elements, mind you, the ionization energy is the amount of energy necessary to remove one electron from the highest energy orbital of such an atom. In the simplest case, if we imagine an isolated neutral hydrogen atom, it would take approximately 1300 kilojoules per mole of energy to remove its electron from the 1s orbital, leaving us with a free electron and a positively charged hydrogen cation. This chart illustrates the trend in the amount of energy that this process takes for different elements. As the atomic number increases, we see this general pattern of increase over a certain interval, followed by a sharp fall before it begins increasing again. What's actually happening here? Notice the high points on the graph all correspond to noble gas elements in pink. Furthermore, the low points on the graph correspond to the alkali metals in blue. Since the alkali metals are the leftmost group of the periodic table, and the noble gases are the rightmost, the trend is clearly that as we go across the rows of the periodic table from left to right, the ionization energy increases. And especially if you compare the noble gas elements, there's another pattern, that as we go from top to bottom on the periodic table, the ionization energy decreases. Overall, the association follows a similar pattern to atomic radius, as discussed at the end of Chapter 5. Specifically, larger atomic radius correlates with smaller ionization energy and vice versa. However, this pattern is not absolute. In particular, if we focus on row 2 and row 3 elements, we can see a couple of exceptions to the pattern. As we move across row 2, from lithium to neon, we first encounter an outlier when moving from beryllium to boron. Despite being to the right of beryllium, boron has a lower ionization energy. The same thing happens to the elements below them in row 3. Aluminum has a lower ionization energy than magnesium, despite being one place to its right. Why does this happen? Boron and aluminum have their outermost electron in a p orbital, while beryllium and magnesium have their outermost electron in an s orbital. Since the 2p orbital, in the case of boron, is higher in energy than the 2s orbital and further away from the nucleus on average, it is comparatively easier to remove. Hence, boron and aluminum have lower ionization energies than predicted by simple periodic trends. We can see another deviation from the pattern in the group 6a elements, which are oxygen and sulfur for rows 2 and 3 respectively. Comparing nitrogen and oxygen first, oxygen has a lower first ionization energy despite being one place to the right of nitrogen. This is explained by the fact that oxygen's outermost electron is in a filled orbital, while the outermost electron in nitrogen is in an orbital by itself. This makes oxygen's outermost electron easier to remove, so its ionization energy is lower. The same trend can be seen when comparing phosphorus and sulfur, which are the analogous elements in row 3. Sulfur has a slightly lower ionization energy than phosphorus, for the same reason as explained above with oxygen. So far, we've looked at what's called the first ionization energy of an element, the amount of energy needed to remove one electron from a neutral atom of that element. It's also possible to measure the second, third, and other subsequent ionization energies for elements as well, where each of these corresponds to the loss of another electron from an already ionized atom. On the screen now, you can see the first ionization energy process at the top, followed by the second ionization energy and the third ionization energy. And of course we can define even higher ionization energies than these, following the same patterns. There's an interesting trend in the subsequent ionization energies for elements, which I'll illustrate with this chart. Here we have a list of all the third row elements in the periodic table, and each row represents their first, second, third, fourth, and so on ionizations. Now, for any element, the second ionization energy will always be larger than the first, the third will always be larger than the second, and so on. This is because each successive ionization corresponds to removing a negatively charged electron from something that becomes more and more positively charged with each step. Since opposite electrical charges are attracted to each other, this becomes harder and harder each time. So for any element on this list, it's not all that remarkable that the ionization energies increase as we move down the chart. What is evident, however, and highlighted in this chart in orange, is that for each element, there is a point at which the ionization energy doesn't just increase, but it increases by a very large amount compared to all the previous ionization energies. Why does this happen? A closer look at the pattern reveals the answer. The jump always occurs between ionization energies where we go from removing an element's valence electrons to removing non-valence electrons. For instance, with sodium, the large jump occurs between the first and second ionization energies because sodium has one valence electron. So the first electron is easy enough to remove, but since the second electron to be removed can't be a valence electron, it's much harder to remove, and a large jump in energy occurs. Looking at one more example, magnesium has a modest increase in energy between its first and second ionization energies, but a much larger one between the second and third ionization energies. Again, this can be explained by the fact that magnesium has two easily removed valence electrons, but the third electron to be removed must be a non-valence electron, and hence much harder to remove. The fact that valence electrons are easily removed compared to non-valence electrons is an important factor in what's called the octet rule, which is the observation that main group elements tend to undergo reactions that leave them with 8 outer shell electrons. In other words, they want to arrive at a noble gas electron configuration, with their outermost electrons being in completely filled s and p subshells. We're going to skip over the details of electron affinity, but suffice it to say that it's a property of an element that measures how easily an electron can be added to that element to form an anion with a -1 charge. This is much easier to do for most nonmetals than it is for most metallic elements. Combining this knowledge with the ionization energy trends from before, we can see that metallic elements tend to have both low ionization energies for their valence electrons, as well as low affinity for adding electrons to their valence shell. As a result, it's easy for them to lose electrons, but much harder for them to gain them. As a result, we now have an explanation for something you've seen already when we looked at ionic compounds back in Chapter 2. Metals tend to lose electrons to form cations when they're involved in reactions. For nonmetals, the opposite is true. They have both high ionization energies for their valence electrons and high affinities for adding electrons to their valence shell. So while it's hard for them to lose electrons, they can much more easily gain one or more electrons in chemical reactions, meaning that they generally form anions. Again, this is something you'll be familiar with from when we first discussed ionic compounds. Let's wrap things up with the subject of lattice energy. Now, we won't be discussing specific calculations of lattice energies using the Born-Haber cycle, so you can ignore that part of this chapter. However, you will be responsible for determining whether different compounds should have higher or lower lattice energies compared to each other. Briefly, lattice energy is the amount of energy involved in holding an ionic solid together. The higher the lattice energy, the stronger the forces holding the cations and anions together. There are two factors at play when it comes to determining lattice energy. The first, and much more important one, is the magnitude of the charges on the ions present in the compound. For instance, looking in the first column, we can see that the lattice energy for beryllium, magnesium, and calcium fluoride are all much higher than the lattice energies for lithium, sodium, and potassium fluorides. This is because the alkaline earth metal fluorides have cations with a +2 charge, while the alkali metal fluorides only have cations with a +1 charge. This trend can also affect anions, which is why the last column, with the compounds containing oxide ions, have much higher lattice energies than any of the corresponding fluoride, chloride, bromide, or iodide compounds with the same cations, again due to oxide having a -2 charge versus the halide anions having only a -1 charge. The second, less important factor is the sizes of the ions. For example, if we look at the three entries at the top of the first column to compare the lattice energies for lithium fluoride, sodium fluoride, and potassium fluoride, let's try to justify the rankings in observed lattice energies. Just like lithium atoms are smaller than sodium atoms, which are smaller than potassium atoms, the cationic forms of these elements follow the same trend. Lithium cations are smaller than sodium or potassium cations, while potassium cations are the largest of the three. Since all of these compounds, lithium fluoride, sodium fluoride, and potassium fluoride, all consist of cations and anions with the same charges, we can't rank their lattice energies on that basis. Instead, we have to use the secondary factor of relative ion sizes. Since smaller objects tend to pack together more tightly in general, it may not be a surprise that smaller ions tend to produce compounds with higher lattice energies when all other factors are equal. Since lithium fluoride, sodium fluoride, and potassium fluoride all have the same exact anion and equally charged cations, the only factor differentiating them is cation size. Lithium, the smallest cation of the three, gives us the highest lattice energy of the three compounds, and the trend continues downward as the cation size increases. That brings us to the end of Chapter 6, and the end of what will be on the third exam. Thank you all for listening, and please continue to stay safe.